The last set of three axioms I call the specialty axioms. That's because they deal with the special role that certain vectors and certain scalars play in a vector space. Okay? And again, the idea is that we want to make sure that some of the special properties of the numbers 0 and 1, that's what I'm referring to, will be reflected here in a vector space. So let's see what they are. The first one is what I call the neutral object axiom. And what it says is that there's got to be an object which we're going to denote by 0 as a vector. Okay, but it doesn't have to be the 0 vector that we're used to, just an object in the set. Okay, so there is an object in our set. We're still going to denote it by 0. Why? Because it has the same property as the 0 vector, namely that for any other object v, if we add 0 to v on either side, of course we're going to end up with the same thing. What are we going to end up with? The same vector v. So this is a special vector that will play the role of the 0 vector in the regular situations where we used to. Okay, but again, remember, this might be something quite different from a 0 something. The second one is the opposite object axiom. So that says that for each object, there is another object which we're going to denote, again, in a familiar way by negative v, so that when we add negative v and v, we end up with the 0 vector. Okay, so first of all, we need the 0 vector, and by using its definition, it doesn't do anything in addition. And then once we have that one, for each object, we want an opposite object, so that once we add them up, we end up with the 0 vector. And finally, and this is the last axiom, if we look at the scalar 1, the usual regular number 1, it has to act neutrally when it comes to scalar product, meaning that for any object v, if I multiply 1 times v, I get v back. Okay? So these are the axioms that are needed. There is only 10 of them. Look at the bright side. There could have been 20. No, there is only 10 to check. Okay? But we're going to need to check all of them to find out if we're dealing with a vector space or not. This is an important issue, so we're going to look at them a little bit more in depth. So some warnings about how to deal with these vector spaces. Okay, so there are many facts that can be proved to be true in all vector spaces. Okay, there are many things, and we're going to see many of them in class as we go through the analysis of these vector spaces. Okay, some of these facts are going to be very simple, almost obvious. We may be tempted to say, well, of course, duh. Other ones are going to be very complex, and they're going to be big discovery, and they should create a response of, wow, who'd have thunk of that, right? But for all of these, we always need a proof. In some situations, especially with the ones that look obvious, you might think, well, I don't really need a proof. Obviously, that is true. But remember that unless we can use logic to prove them, we cannot assume that they are true. In fact, we're going to see that there are some facts that are obvious, but in fact are not true. Okay, so we're going to give you some counter examples of things that you thought you knew all your life, but turns out that they're not really part of the reality of vector spaces. They may be true for real numbers, they may even be true for regular Euclidean vectors, but they're not true in vector spaces in general. So this is, keep in mind that we're dealing with abstract algebra, so some of the things that we have taken for granted that were coming from the practical side of numbers, they may not be true in the abstract sense, so we always have to check all of them.